Welcome to my classroom. In this chemical process calculation course, we have been discussing about thermophysics and thermochemistry. In the previous lecture, we have solved numericals on how to determine the heat of formation, heat of the reaction, specific heat, if specific heat is a function of temperature, how to determine the average Cp or Cp mean, all that we have discussed. So in this lecture, we are going to determine the adiabatic flame temperature. In the previous lecture, we have discussed the theory part of what is adiabatic flame temperature. So, what are the heats, that how many enthalpies are involved when there is adiabatic condition existing in the system. For example, in a combustion chamber, when the system is under adiabatic condition, there is no net heat flow from the system to the surrounding or from surrounding to the system. That is, del Q is 0. Then there are only three enthalpies involved in it. One is enthalpy of, so I have told you that we are doing this performing this calculations of heat of the reaction only at 25 degrees Celsius as standard condition. So what we can do is, when the reactants are entering at a temperature T, we can first enthalpy involved in the enthalpy term involved in the equation for determining the adiabatic flame temperature is enthalpy of the reactants, right? That to reduce the temperature from T1 to standard temperature of 25 degree Celsius. So that way that we have MCP delta T coming into picture. So CPTLU is known, and T reaction temperature is known. We know T2 is reference temperature 25 degrees Celsius or 298 Kelvin. So how much mass of reactants are there, how much moles of reactants are there, based on that we can find out the enthalpy of the reactants. Okay, so enthalpy of reactants to reduce the temperature from T to 25 degrees Celsius can be calculated. And if the reactants are entering at 25 degrees Celsius, then this term is going to be 0. That is, enthalpy of the reactant is going to be 0 if we are having these reactants entering at reference temperature itself. That is important point. Okay, and then we have that is delta H1. Second delta H is H3 minus H2, which is the heat of the reaction, because at 25 degrees Celsius what is happening, we are allowing the reactant to get converted into products. So that way here the delta H is equal to delta HR at standard condition. You can say delta HR not. Okay, so that way we know heat of the reaction at standard condition. Even if it is not known, from the basic heat of formations also we can determine what is the heat of the reaction. Okay, so if you know the heat of the reaction per mole or per kg, based on how much moles of reactants are there, we will get what is the heat of the reaction required for how much heat is evolved or how much heat is absorbed. It may be exothermic reaction or endothermic reaction. Based on that, we are going to have this second enthalpy term value is going to be equal to delta HR multiplied by number of moles of reactants, or number, if it is Cp values are given in kilojoule per kg, heat of the reaction is given in kilojoule per kg, then in that case we have to multiply by number of mass. Okay, mass of the reactants present. Okay, so two terms are over. Then we have third term, which is heat to be added to raise the temperature of the products to the final temperature or adiabatic flame temperature T. Okay, so that way we are having a third term, which is also again a sensible heat or sensible heat, which is required to the heat required to raise the temperature of the products from 25 degrees Celsius to adiabatic flame temperature T or final temperature T. Okay, so this is the case. So for that again MCP delta T, what is the delta T here? Final adiabatic flame temperature T minus reference temperature 298 Kelvin, that is our delta T. Cp value, it may be given as Cp mean, or Cp may be given in the form of A plus Bt plus Ct square. So then we are going to make use of integration method, integral Cp dt from T 298 Kelvin to T adiabatic flame temperature. Okay, so that way we can equate these three terms and obtain the adiabatic flame temperature. That is one method. So there may be other type of numericals where this adiabatic flame temperature is given, but we have to determine the what is the percentage excess air used, because theoretical air requirement we know how to determine actual air requirement if excess air is given. So from our actual oxygen requirement we can determine what is the associated nitrogen. So we can do the material balance for what is the composition of the reactant, and we can do flue gas analysis and write what is the composition of the product, right? So same, whatever we have learned in material balance are going to be used here also. Okay, so we cannot say that module 1, module 2, module 3 I don't remember. So we have to refresh whatever we have learned in the previous models and we make use of those concepts in this module. Okay, let us solve numericals on adiabatic flame temperature. Okay, be ready with your calculator and notes. Ready? So we can do some numericals on. So far what we have done is we have determined the heat of the reaction or enthalpy of heating only, but no reaction was involved. Now we can do numericals on heat of the reaction determination once Cp values are known. Okay, so particularly determining the adiabatic flame temperature. So I have told you in the previous lecture as well as the beginning of this lecture, I have told you that uh, the reaction may be taking place from at a temperature. For example, reactant may be at a temperature T1 and the final products may be at a temperature T2. Okay, it may be depending upon it is exothermic or endothermic. There may be temperature rise or decrease in the temperature. Okay, but what I have told you is the data, the heat of standard heat of formation or standard heat of the reaction data will be available at 25 degrees Celsius. This standard conditions of 298 Kelvin and zero point 0.1 megapascal. Most of the heat of the reaction data are available. That's why it is always easier or convenient to calculate the heat of the reaction at 25 degrees Celsius and whatever is the temperature given for the reactant. For example, reactant is available at a temperature of reactant is let me say there are three reactant A, B, and C with the specific heats A, CPA, CP of A, CP of B, CP of C. It may be directly we may have the data CP mean, or it may be a function of temperature. So whatever we will have, if there are three components, we are going to have respective specific heat values. Let these reactants are initially at a temperature of T1 Kelvin, and the final products are at a temperature of T2 Kelvin. So the what is delta H of the reaction is can be directly also obtained. What that and that can be equal to if you are first reducing the reactant to, for example, let me say we are having heat of the reaction data at standard conditions of 298 Kelvin and zero point 0.1 megapascal. So what we can do is we can calculate in this fashion instead of directly calculating what is the delta H of the reaction. What we can do is we have already the heat of the reaction at this temperature. Only if you multiply by mass, if you know delta H of the reaction, how many moles we are producing, multiplying that we are going to get net heat that of the reaction for a given mass or given moles. So what we can do is we can find out what is the heat that is to be liberated or removed from the reactant to cool it from a temperature of T1 to the standard temperature of 25 degrees Celsius or 298 Kelvin. So we are going to have a sensible heat calculation of MCP delta T. So Cp of A, Cp of B, Cp of all the reactant has to be taken into consideration. So what we are doing is we are actually reducing the temperature of the reactants to 25 degrees Celsius. How much heat has to be liberated? So we can find out what is the delta H here, right? So then what will happen? We can allow the reactions to get converted into products PQR. So what we are doing, we are reducing the temperature of the reactants from T1 Kelvin to 298 Kelvin. What is the heat, sensible heat associated with it can be calculated as delta H of the reactants. Okay, then we can calculate the delta H of the reaction that is at standard condition. Delta H are not, that is 25 degrees Celsius. So what we are getting is products are formed at this temperature. So then this products has to be reach this temperature of T2 Kelvin. So for that we have to supply heat. How much heat needs to be supplied to raise the temperature of these products P, Q and R to heat it to a temperature of T2 Kelvin. So once what is that one? So that again delta H of the products. So MCP delta T comes into picture, that is T2 minus 298 Kelvin will be the delta T. So accordingly we are going to get the values of delta H for the reactants and delta H for the products. In addition what we have is delta H for the reaction. So what we have here is delta H of reaction. Okay, so there are three steps involved in this type of numericals. First, we will determine how much heat is to be removed to reduce the reactant temperature from T1 to this 298 Kelvin. Okay, so how much this that heat can be calculated by MCP delta T or NCP delta T by either by integration method, or if Cp mean is given, is simply MCP delta T we can calculate. Second step is heat of the reaction at standard condition, that is 298 Kelvin. This can be given or taken from the literature. What is the delta H of the reaction? Otherwise also from heat of formation, from its pure elements also we can find out what is the delta H, right? So we should have the data information of delta H of the reaction per kilomole. Then for the given moles, so how much is the number of moles of A, B reactants or products are there? Accordingly, we are going to multiply it to get how much kilocalories or kilojoules are there. Okay, so that is done. Second step, and third step is heating the products from the temperature of 298 Kelvin to the T2 Kelvin. Okay, so that will be how much heat needs to be added. So that will come under temperature of the products from, okay, raising the temperature of the products from 298 Kelvin to T2 degree Celsius. What is to be done? Okay, so how to calculate the delta H of the reactants? So if you have, there are I components are there. If CPI is the specific heat capacity of the ith component, then its mole fraction, number of moles multiplied by CPI of compound into dt. Okay, so that way we can calculate by doing the summation, how whatever may be the summation. So if you know, the already we did a numerical, right? A, B are there. A is some 25 moles, B is 75 moles. So we can say 25 into Cp of A. If it is 75, so you can say 75 into Cp of B, right? So that way we can calculate, multiply by the respective numbers to get what is the total this thing. Okay, so that can be done. Same thing can be done for products also. And heat of the reaction will be heat of the reaction at a given temperature is equal to heat of the standard heat of the reaction plus these two. So this is the final equation we should have. So, okay, so heat of the reaction should be this thing. Okay, but at adiabatic conditions, this is the condition we can solve the problems for adiabatic flame temperature, because del Q equal to 0. So that's why only the three heats are involved. One is enthalpy of the reactants, enthalpy of the products, and then heat of the reaction. So these three terms will constitute our final expression to determine the unknown parameter like adiabatic flame temperature. Or if adiabatic flame temperature is given, we should able to calculate the excess air percentage. Okay, so such type of numericals we can solve. So we have last class itself we have seen what is a adiabatic flame temperature. Okay, so take on this problem. Calculate the theoretical flame temperature of carbon monoxide burnt at a constant pressure with 100% excess air. The reactant enters at 95 degrees Celsius. Remember, if the reactants are entering at 25 degrees Celsius, in the diagram what we have seen, that delta H of the reactant is 0. Okay, that is enthalpy heat. No heat needs to be liberated to reduce the temperature from 25 to 25, right? So that way, if a reactant enter at 25 degrees Celsius, then you are going to have delta H of the reactant equal to 0. Similarly, if the products also is at 25 degrees Celsius, then delta H for the products is going to be 0. Only delta HR is going to be there. So carefully read the temperature of the reactant as well as the products. Okay, so here reactants are entering at 95 degrees Celsius. So standard heat of the reaction is given minus 67,636 calorie per mole, and Cp mean value is given as calorie per moles degree Celsius. So air value, air is given, mean out of the reactant we have to consider it to be air instead of individually considering how much oxygen and nitrogen. Okay, so carbon monoxide, carbon dioxide, oxygen and nitrogen, Cp mean values are given, so we can determine the theoretical flame temperature. Okay, So how to solve this problem? So I have explained you the procedure. So you should take a basis because no moles are given. So we can take a basis of 1 gram moles because Cp value is given in moles, so we can take gram moles itself. If it is given kilomoles, so you can take in kilomole basis. Okay, 1 gram mole of carbon monoxide. So that is our A. Carbon monoxide is the reactant. So we know what is the reaction taking place, right? Carbon monoxide combustion is CO plus O2 giving CO2 and delta HR is given. Delta HR is given as minus 67,636 calories per mole. So to if 1 gram mole of carbon monoxide is burned, so this is the delta heat of the reaction. Okay. Now we can calculate. We can write the material balance thing, right? What is that? 1 gram mole of CO will react with half is 0.5. So 0.5 gram mole of oxygen to form 1 gram mole of CO2. Remember, first step is to find out the flue gas analysis. Okay, so we should know what is the composition, how much moles exactly, not even percentage. Amounts we should know. That's why first step is like material balance problem, what we have done, how to do flue gas analysis or set gas analysis. That we have to do same thing here. 1 gram mole of, here basis itself in gram mole, so no need of multiplying by molecular weight. So here what is our basis is 1 mole gram mole only, so that is our thing. So that means we have what is the theoretical oxygen demand. Theoretical oxygen demand is 0.5 gram moles of oxygen. Remember, it is complete reaction, proceeds to 100% conversion we are considering. So that way, and there are no side reactions, so directly we are getting what is theoretical oxygen demand. Then what is it is given, no, excess percentage is given. I gave you a formula, right? So how to calculate y? One is y 1 plus z by 100, where z is percentage excess here. So it is given 100% excess here. So that means we get y equal to 2. Okay. So that is multiplying factor. What is actual oxygen demand then? Actual oxygen demand is y into theoretical oxygen demand. So that is 2 into 0.5. We have 100% excess. That means instead of 0.5, we are sending in 2 times 0.5. That is 1 gram mole. 1 gram mole of oxygen is supplied. Okay. So now, how much is the oxygen is oxygen is 1 mole, means how much is nitrogen, or we can say what is the air. Okay, so we can say that 1 gram mole of air, 1 gram mole of air will contain 0.21 gram mole of oxygen. Therefore 1 gram mole of oxygen means 1 gram of oxygen means how much air is required. Okay, so that we can do, right? So 1 divided by 0.21, 1 into 1 divided by 0.21, which is equal to 4.762 is the gram moles of air. Why I am doing it in air term? Because Cp value is given in this problem as air. Cp of air is given, so I have to consider the reactant as air. That's why I have calculated what is the amount of air. We can find out what is the actual nitrogen entered is equal to 4.762 air minus oxygen. Oxygen value is 1, right? So that means 3.762 gram moles of nitrogen is entering the system, and the same amount is going to be the amount of nitrogen in the product. Okay, and how much moles of now what is your oxygen consumed in the reaction? Your theoretical oxygen, excess oxygen, I can say directly, excess oxygen is equal to actual oxygen entered minus theoretical oxygen, right? Actual oxygen entered is 1 mole. Theoretically we want only 0.5, so the excess amount is 0.5 gram moles of oxygen. Now we know exactly how much products are formed. You can see here there are, we can write the composition now. Okay, so for feed, how much gram moles, for products, how much gram moles can be written clearly. Okay, so what are the reactants? Here reactants are carbon monoxide and air. Okay, so what are, how much gram moles of feed is having? Feed is having actual air. Actual air amount is 4.762. So how much air is entering? Sorry, air is 4.762. Carbon monoxide is 1. That is our basis actually. Okay, so this is the gram moles, n values for this thing, right? So you can calculate Cp of, you can calculate the values now. Okay, so how to calculate? Now similarly you write for products also. In product, what are the constituents? In product there is no CO because 100% conversion, CO is 0. Okay, so we are not writing CO here because 100% conversion. If it is not 100% conversion, there will be CO present in the product. Okay, so that's why I am writing and striking here. So what are the products then? CO2 is there. How much CO2 is formed? From the reaction we have 1 gram mole of CO2 is formed. Okay, so CO2 formed is 1 gram mole, and it will contain that excess oxygen and it will contain the nitrogen, right? So what is the excess oxygen? We have calculated it to be 0.5 gram mole. How much nitrogen? Whatever has entered will be present in that 3.72 gram moles. Okay, so that way we are having the composition of the feed as well as composition of the products, and data are given in terms of Cp value, right? So that diagram you recall. So what we have to do, it is 25 degrees Celsius. The feed is entering at 95 degrees Celsius. So we have to reduce the temperature from 95 to 25. Okay, so delta H of the reactant can be calculated as, so how to calculate, so that you can do. Similarly, the products are at, what is the product temperature? We have to determine, that is our adiabatic flame temperature. We let us say adiabatic T is the adiabatic flame temperature. We don't know what is that. So in the right hand side, here reactant, here we have products. So this temperature is how much we don't know. This is 25. So here delta T is 95 minus 25. Here delta T is T minus 25. Okay. So but accordingly we will calculate that, and we know what is delta H of the reaction at this temperature 25 degrees Celsius. We have the data. So this delta HR, this delta H of the products and delta H of the reaction, summation should be, algebraic sum should be equal to 0 because delta Q is equal to 0. But you have to, whether it is exothermic or endothermic, you have to take into account. So heat is liberated or which is attained, we should take care of the convention. Sign convention should be taken care. Okay, so shall we determine the delta H of the reactants? Now delta H of the reactant is 1 into Cp of CO plus 4.762 into Cp of air multiplied by delta T gives us the delta H of the reactant. Okay, so delta H of the reactant, I am writing in detail because this is our first problem. A number of moles of NCO into Cp of CO plus, again dt I am taking common, so NCO CPO plus N of air into Cp of air into delta T, that is 95 minus 25 degrees Celsius. Let me say temperature of the reactant minus temperature of this reference. Okay, so that way if you substitute, number of moles of CO is 1 multiplied by CO multiply by CO of this one plus number of moles of air is 4.76 into this, okay, into 95 minus 25. Let us substitute the value. Cp of CO is given 6.98, Cp of air is given 6.993. Okay, so substituting, you will get a value in terms of calories which may be around 2617.4 calories. Okay, similarly, delta H of the product can be determined. Delta H of the product can be determined. What are the products? We have CO2, oxygen and nitrogen. How to determine that? Cp of the products, I will determine directly delta H. Okay, let us do it separately. Cp of the product is equal to number of moles of CO2 into Cp of CO2 plus number of moles of oxygen into Cp of, here we are not doing it in air, right? Because the quantity is not in proportion of air, plus N into number of moles of nitrogen into Cp of nitrogen. So that is 1 into 12.94 plus oxygen is 0.5. So 0.5 into 8.35 plus nitrogen is 3.76 into Cp value is 7.92. So this gives us Cp of the product which comes out to be 46.895. Okay. So once we have the Cp value, we can calculate the delta H of the product. Delta H of the product is equal to, this we have calculated separately, right? So that way 46.895 into, we don't know the temperature, right? Final temperature we don't know, but reference temperature we know. So that way we have delta H of the product is known. Okay. And what is the other thing? What is the reaction taking place at the 25 degrees Celsius? So we have delta H of the reaction at 25 degrees Celsius, which is given as minus 67,636 calories per mole. Okay. But what is our basis? We have for 1 mole. So delta H multiplied by 1 mole. So we will get this much calories. So delta H of the reaction, because in this particular case we have only 1 mole, but otherwise we are going to have, we will have a multiplying factor of what is our basis. Okay. So we are having minus 67,636 calories only. So that's where this mole getting cancelled. So this is the total heat. So now what you can do is total heat released. Total heat released can be determined. Okay. Total heat released is equal to make summation of the things. Okay. So what we'll have is total heat released is equal to this value. What is that? 67,636. This is in minus. Okay. This is also is going to be in minus. Okay. Because this heat is to be removed. Heat to be removed. Okay. So that way both will come as 70 to 53.4. Okay. And this should be equal to delta H of the products. Okay. This is equal to 46.895 into T minus 25. Substituting, we get, since del Q equal to 0, the summation should be equal. So we have T is the only unknown parameter. So what you will get is T minus 25 is equal to 70 to 53.4 by 46.895. So we can take it to the right hand side. You will get T is equal to this much degree Celsius. So you will get around, use your calculator and comment your answer. Okay, so you will be getting more than 1200 degrees Celsius, but less than 1600 degrees Celsius. Okay, so this is the way we have to solve the adiabatic flame temperature problems. Okay, so we have another problem for practice. We have dry methane. Take down. Dry methane is burnt with dry air, both being initially at 25 degrees Celsius. So here delta H of reactant need not be calculated. That is no need of heat to be removed. The theoretical flame temperature is 1570 Kelvin. Here flame temperature is given. If combustion is complete, find the here also 100% conversion taking place. Find the percentage excess air used. Okay, so heat of the reaction is given. Cp mean values are given in joules per mole Kelvin, but delta HR is given in kilojoule per mole Kelvin. Please note the difference. Okay, so we can solve this problem now. Okay, I'll just tell you the procedure so that you yourself can solve, because this is the first time you are doing a problem for y value, how to do this y value, right? So here excess here, so I have always defined you how to use that one. Let z be the, let z percentage be the thing, then y is equal to, that is excess here, that is a multiplying factor, is equal to, where we will define it is, if you know theoretical oxygen demand, actual oxygen demand is equal to y times TOD, where y is equal to 1 plus z by 100, where z is the percentage excess here. Okay, so this y value we don't know right now. We are going to find y, where t is given, find y. That is the problem here. Okay, so what we can do, we can take a basis, same 1 mole it can be taken, because data are given in mole only, so no need to go for kilomole basis. So we can take a basis of 1 gram mole of methane, dry methane. Okay, and it is burned with the dry air, both is initially at temperature of 25 degrees Celsius, and the adiabatic flame temperature is given 1570 Kelvin. Okay, so reactants are this, so this is 0. Okay, H of reactant is 0, because we given that it is at 25 degrees Celsius. So delta HR is taking place at 25 degrees Celsius. So obviously we have to heat and find out the delta H of the products. Okay, or enthalpy of the product, enthalpy of the reactant not required. So this we have, you should know, let Z percentage is the excess air used. Okay, then y is equal to 1 plus z by 100. Okay, so we can write the reaction now. What is methane burnt means, CH4 will be burnt with oxygen to form, you know, all hydrocarbons, combustion products are carbon dioxide and water, balance it, 2 is here, 4H is there, so 2 plus 2 4. So we have, what I can write is 1 mole of CH4 reacts with 2 moles of oxygen to form 2 moles of CO2 and 2 moles of water. Okay, so that means what is our theoretical oxygen demand is equal to 2 moles, because this is our basis. Our basis is 1 gram mole of methane. Okay, so TOD is 2 moles of oxygen right? Here itself oxygen is there. Okay, theoretical oxygen demand is 2. Then what is our actual oxygen demand? Actual oxygen demand is 2 times, sorry, y times theoretical oxygen demand, so which is equal to y into 2. You can write like 2y. So actual oxygen demand is 2y. Then what is your actual air demand? Actual air is equal to same procedure like previous problem. Okay, actual air is 100 mole of air will contain 21 moles of oxygen. So here we have 2y moles of oxygen. So therefore how much moles of air is required? That is 100 into 2y by 21. So which will get like 2y by 0.21. How much? You will get 9.524y is the moles of air required. Remember, we are getting it as a function of y only because we don't know what is y. Okay, so that is our aim, right, to determine the y value. So then now we know actual oxygen is 2y, actual air is 9.524y. Then what is your actual nitrogen entering? Actual nitrogen entering is total air is, that is 9.524y minus 2y. So that is 7.524y is the moles, this much moles. 9.524y moles of nitrogen is entering the system. And then we can write what is the oxygen, excess oxygen. Excess oxygen is equal to actual oxygen minus theoretical oxygen. Actually how much oxygen we are sending? We are sending 2y oxygen, but really how much oxygen we need? Only 2 moles we need. So that way 2y minus 2 moles of oxygen is the excess oxygen present. Okay, so now we can write the composition. Now we know how much reactants are there, how much products are there, how much excess oxygen is there. All data we know. So what we can do is, so we have already seen 2 moles of CO2 is formed, 2 moles of water is formed, right? So with that what we can do, we can write the composition of the reactant and products. So we can write the composition of the reactants and products. So in reactant what are there? Dry methane is there, and then it is burnt with oxygen and nitrogen. Here I am not writing air because Cp of air is not given. Simply oxygen, nitrogen Cp's are given in the data. That's why, because Cp of air is not given, I have written like oxygen, nitrogen itself, because Cp of oxygen and nitrogen is given. Okay, so how much moles of methane is there? That is our basis. So we know 1 gram mole. How much oxygen is entering? We know that is 2y moles, right? So actual oxygen entering is 2y moles. And how much nitrogen is entering? 7.524y gram moles. Okay, so what is the product composition? Products are, it is again 100% composition, 100% conversion. There is no methane. Okay, because 100% conversion. If it is not 100%, there will be some unreacted methane. Okay, then how much, what are the products here? CO2 is the product, water is the product, and whatever is the excess oxygen, and then whatever is the nitrogen. So how much kg moles? So CO2 we know how much moles directly, right? 2 moles and 2 moles of CO2, 2 moles of CO2 and 2 moles of water is direct value, but excess oxygen is this 2y minus 2, 2y minus 2 moles of oxygen is there, and whatever is the nitrogen that has entered will be inert. That's why that is going to present in the products also. Okay, So now what we have to do? We have to make the balance. What is that? We know delta H of the reactant plus delta H of the reaction is equal to delta H of the product, right? So that is a balance for adiabatic conditions, right? For adiabatic system, del Q equal to 0. So we have this. We have to take care of sign conventions. Okay. So in this case, it is 0 because feed is at 25 degrees Celsius. Okay. So delta H of the R has to be calculated, and delta HR is given 801 kilojoule per. So it is given 801 kilojoule. It is given. So if you put 0, it will be joules per moles degree Celsius is equal to delta H of the product. So this we have to determine now. Okay. So there is only unknown parameter. If you calculate this value, we will have a function of y. Y can be simplified to y. This expression can be simplified to obtain the y value. Okay. So can you calculate this value? MCP delta T formula we have to do. Let us calculate CP value. What is the delta P of the product? You can calculate. That is how much moles are there. We have to see first. Okay. So how much CO2 is formed? Is it 1 or 2? Sorry, this is 1 moles only, right? Okay. So that way we can calculate delta H of the product. Delta H of the product is equal to, can calculate MCP mean into delta T. Okay. So summation of MCP delta T, we can get that value by multiplying by the respective values. This is 1 mole of CO2. For CO2 value given is 51.79 plus 2 moles of water, corresponding value is 40.19 plus 7.524 into y is the nitrogen value. Its corresponding value is 32.15 plus for oxygen it is given 2y minus 2 is in amount, and for it value is given as 32.4. Please check it. So what you get is in this CP value, CPDT CP value. So then we can multiply by delta T. What is delta T? 1570 minus 298 Kelvin. Remember that in the question it is given in degree Celsius. We have to convert to Kelvin, right? 50. Okay, 1570 Kelvin is given. So 1570 minus 298 Kelvin. So we get this equation, and this should be equal to this. Okay, so whatever we get as delta H of the product. So what you get is, simplify it. So if I simplify it, what you will get? 51.79 plus 40 into 2 around 80.38. Okay, plus, so 30, if you multiply this 64.8 into y minus 32.4 into 2, it is 64.8. So this is taken care. Okay, 2 into 40 is taken care. This is taken care. Then this time 32.15 into 7.524 is almost 241.9 into y. Okay, so this multiplying we get this equation, and this all this equal to, this is the value, so we can write this is equal to 80100. Okay, kilojoule it was given. We are converting to joule because this side it is joules per mole Kelvin. Okay, so now we have an expression. Okay, simplifying for y, you will get the answer for y. Okay, so what you will get is, so if you take it to the, you have delta t here, don't forget, into delta t is 1570 minus 298, which is almost 300, so 1200 around 1272, right? So if you take it to the left hand side, you have 801 by 1272 equal to, simplifying for y, you'll get 306.7 into y plus 67.37. Then we will have y is equal to 1.8335. Okay, so which can be written as 1 plus 0.8335, which is 1 plus 83.35 by 100. So we know that y is equal to 1 plus z by 100. So we can say that percentage excess air is 83.35 percentage. Okay, so that way we should able to solve the adiabatic flame temperature problems. Either if excess air is given, we should able to determine adiabatic flame temperature, or if excess adiabatic flame temperature is given, we should able to determine the percentage excess air. Okay. So take down this problem. Please go through what is given. Calculate the adiabatic flame temperature of gas mixture consisting of 20% carbon monoxide and 80% nitrogen when burnt at constant pressure with 100% excess air. So in this case, excess air percentage is given. We have to determine what is the adiabatic flame temperature. The reactants, both gas and air, are entering at a temperature of 298 Kelvin. So here so that means heat required to reduce the temperature of the reactants from the given temperature to standard temperature is going to be 0, because the reactants are entering at the reference temperature only, right? The standard heat of the reaction delta HR naught is given minus 283.178 kilojoule per gram mole it is given. Okay, and the heat capacities are in joule per mole Kelvin. Remember, standard heat is given in kilojoule per mole Kelvin, whereas heat capacitors are in joule per mole Kelvin, where the components of CO, it should be CO. Okay, CO2 26.54, 45.45 into 10 power minus 3 minus 14.298 into 10 power minus 6, whereas oxygen 25.61, 13.26 into 10 power minus 3 minus 4.208 into 10 power minus 6, nitrogen 27.03, 5.812 into 10 power minus 3 minus 0.289 into 10 power minus 9. Carefully you see here, for these two data, C data is in 10 power minus 6 and for this it is in 10 power minus 9. Please note that. Okay, so we shall solve this problem now. Okay, look at it. So what is that? So in generally, if you want to calculate the adiabatic flame temperature, what we will do? Delta H of the delta H is equal to H2 minus HR, that is H2 minus HR, and delta H3 minus H2 plus H3 minus HP. That is HP minus HR is equal to HP minus HR is equal to, you can say H2 minus HR, H3 minus H2 plus HP minus H3, which gives us HP minus HR, right? So that way here the first term is 0. This H2 minus HR is 0 because the reactants are entering at 25 degree Celsius. Then what is H3 minus H2? That is the reaction here reaction is taking place, no change of temperature. So delta H of HR naught at 25 degrees Celsius, which is given. Per mole it is given. So if you know what is the total number of moles of the thing, we can calculate that. Okay. And similarly, HP minus H3, in that case, we have to make CP data is given in the form of function of temperature. So we have to make use of NCP dt varying from 298 Kelvin, which is reference temperature, to adiabatic flame temperature T. And here we have to determine what is T, right? So that is our task. Task is, let T is the, if T is the adiabatic flame temperature, so use by equating these all the three terms. Okay, so we are going to get the unknown parameter, that is adiabatic flame temperature. ABC value for CO2, oxygen and nitrogen are given. Okay, so we will make use of them. Okay, start solving this. If you understood the procedure, try it yourself. Here we have to find out adiabatic flame temperature. Okay, so let it be T Kelvin. Adiabatic flame temperature. So T is the temperature, that is this one. So this feed is entering at 25 degrees Celsius. So we are having delta HR naught at 25 degrees Celsius is given to be minus 283.178 kilojoule per mole Kelvin. So delta HR is given minus 283.178 joules per mole. I am writing without kilo because other day CP value we are going to substitute in joules per mole Kelvin for unit consistency, since reactants are entering at, since reactants are entering at 25 degrees Celsius. So this term is 0. So that is H2 minus H1 equal to 0. That is delta H of reactant is 0. Okay. Now what is delta HR? So let us first go for basis. So data is given in gram moles only. So let us write 1 gram mole of carbon monoxide, sorry, 1 gram mole of gas mixture. If we consider, okay, if we consider 1 gram mole of gas mixture as the basis, but it is given that it contains only 20% of carbon monoxide. So this gas mixture contains 20 mole percent carbon monoxide and 80 mole percent nitrogen, that is inert, right? So it won't take part in the reaction. So out of 1 mole we have considered as a basis, only 0.2 moles of carbon monoxide is taking part in the reaction. Okay, remaining 0.8 mole of nitrogen is not taking part in the reaction. So this will be in final product, right? Can we write what is the material in a theoretical oxygen demand for this 0.2 moles of carbon monoxide that is taking part in the reaction? What is the reaction? Carbon monoxide, if burnt, means it will form CO2. So if we balance it, we are going to have like this. So for every 1 gram mole of CO, there will be 0.5 gram mole of oxygen requirement to form 1 gram mole of CO2. But how much gram mole we are having in this reactant? So in our system we have only 0.2 gram moles of carbon monoxide. So that means 0.2 into 0.5 by 1, how much? It is 0.1 gram mole of oxygen. So obviously we are going to have 1:1 ratio, that is 0.2 gram mole CO will form 0.2 gram mole of carbon dioxide. Okay, so what is our theoretical oxygen demand here? Theoretical oxygen demand is 0.1 gram mole, and in this question it is given, we have 100% excess here, right? So it is given that 100% excess here is there. So z equal to 100%. So we know y equal to 1 plus z by 100 equal to 1 plus 1, which is 2. So you know actual oxygen demand equal to y into TOD. So y is 2 times 0.1 gram mole. So we have 0.2 gram mole of oxygen is our actual oxygen. So what is our excess oxygen? Excess oxygen is equal to actual oxygen minus theoretical oxygen. 0.2 minus 0.1, again it is 0.1 gram mole of oxygen. So this will be present in product. So this will be present in product, excess oxygen. And what is the associated nitrogen in air? So what is your actual oxygen? So actual oxygen is 0.2. Actual oxygen is 0.2. Then what is our actual air? So actual air is, we know that 100 moles of air will contain 21 moles of oxygen. So that means what is our actual air requirement? Actual air requirement is, so for our 0.2 moles of oxygen, it is 0.2 into 100 divided by 21 moles of air. How much? So that will be our air requirement. 100 into 0.2 divided by 21 is 0.953. 0.9524 moles of air is required. So then what is the nitrogen associated with it? Nitrogen is equal to this minus this, right? Air contains oxygen, nitrogen is equal to air. If oxygen is 0.2 and air is 0.9524, so we can write what is our nitrogen. So nitrogen is going to be 0.7524, right? 0.9524 amount of air minus amount of oxygen, which is 0.7524 moles of nitrogen. Then what is this? We have already seen the feed itself there is a nitrogen. We have seen that feed contains 80 mole percent nitrogen, which is 0.8 moles, right? We have in the feed 0.8 moles. Feed has 0.8 moles of nitrogen plus air has 0.7524 moles of nitrogen. So that will be the total nitrogen entering the system. Total nitrogen entering the system is nitrogen in the feed, that is reactant, plus nitrogen in the air. So that is, we can say 0.8 plus 0.7524 equal to 1.5524 moles of nitrogen, and this nitrogen is going to be present in the product. Okay, so here also we are assuming complete combustion. So what is the composition of the product? We can write, right? So the composition of product will be composition of the product is the flue gas analysis. So what are the products we have? Do we have any reactant? No. Complete combustion, no reactant. So CO is 0. Okay. CO2 formed is 0.2 moles. Okay. So how much excess oxygen? Excess oxygen we have calculated, that is 0.1. Theoretical we have calculated the excess oxygen, which is 0.1 gram mole of oxygen, and nitrogen is 1.5524. Okay, so this is our product composition. Delta HR was given, and we know how much is our reaction taking place. Only 0.2 gram moles of CO2 is taking part in the reaction, and delta HR is given. right? So delta HR was given, right? Yes, delta HR is given minus 283,178 joules per mole. But how much moles we are having? How much moles of CO is reacting? Only 0.2 moles. So multiply by 0.2, we will get what is delta HR naught. Okay. So we can write delta HR naught equal to whatever is the data given minus 283,170 into 0.2 moles. So this is in kilo, multiplied by 3, we did joules per mole, and 0.2 mole. So what we get is this much joules. Okay, so that is going to be, use a calculator, 283,170 into 0.2 equal to 56. Check the answer, 56634 I am getting. Okay, so this much joules we are having as delta H of reaction. Okay, now we have to determine what is the CP value of product. Okay, CP of product is what is the enthalpy delta H of the product is equal to how much product is there. Okay, we are having three products, let it be A, B and C. It's NCP delta T. Okay, so we can say NCP dt Na CPA dt plus NB CPB dt. So your temperature range is 298 and we have assumed it to be T. Okay, so we can write the range also plus number of moles into Cp of C into dt 298 to T. Okay, so how our Cp are given in the form? Which form it is given? Cp is equal to A plus Bt plus Ct square, it is given. So what we can do? We can do the integral, right? So if you do it for Na Cpa, okay, so what we will have is, we already seen that if we integrate this integral, if you are integrating Cp dt, what will happen? Integral dt, what will be the integration product? We are going to get like A into T minus T2 minus T1, right? What is T2 minus T1? It is T minus 298 plus B by 2 into T square minus 298 square plus C by 3 into T cube minus 298 cube. Okay, so similarly we are going to have three terms for all the A, B and C. Okay, so in general what we can write is, this is the general equation, right? So for any component I, Ni into A of I plus B of I, C of ith component, right? So this is general formula. If you have Cp of ith component given in from temperature 298 to T. Okay, so this is formula we can substitute to get in this equation, right? General integration only, it's simple integration. If you perform the integration, what we will get is, we have Na, Nb, Nc value from the product composition. So this is your Na value, this is your Nb value, this is your Nc value. Okay, for each value we are having the ABC value is given. Okay, so with ABC value given, we should able to calculate the values. Okay, how ABC value are given? So here ABC value are given. So with the ABC value is given, please do the delta H of the product. So what we can do is we can write delta H of the product is equal to Na is 0.2. So we have Na equal to 0.2 into, if we integrate, we are going to write like this: A into T minus 298. What is A? 26.54 into T minus 298 plus 45.45 into 10 power minus 3 into, if integrate, we will get T square minus 298. Okay, and minus 14.298 into 10 power minus 6 into, okay, remember this will be divided by 2, this will be divided by 3. So in that integration will come, no, T becomes, A becomes AT, then substituting the limits T1 minus T2, we get this one. So there will be B by 2 and C by 3. Okay, T cube minus 298 cube. So this is 0.2 terms. So this is for component A, which is having 0.2 moles CO2. Okay, similarly we have to write two more terms for oxygen. Oxygen is 0.1 moles, and similarly we have nitrogen 1.5524. Please write the A value, B value, C value given. So A value, B value for oxygen. A value is 25.61. We have 25.61 plus 13.26 into 10 power minus 3 by 2 into, so 25.61 into T minus 298 25.61 into T minus 298 plus 13.26 into 10 power minus 3 divided by 2 into T square minus 298 minus 4.208 into 10 power minus 3 by 3 into T cube minus 298 cube. Okay, similarly for third term also we can write 27.03 into T minus 298 plus Bi by 2. Bi is 5.812 into 10 power minus 3 by 2 into T square minus 298 square. Okay, and finally we have minus 0.289 into 10 power minus 9 by 3 into T cube minus 298 cube. Okay, so we have delta HP term equal to this much. Okay, and if we are adding this delta H of the reaction and delta H of the P should be equal to 0. Okay, so this should be equal to 0. How much we have calculated delta HR? 56360, right? What was given? Sorry, okay, we have calculated that one. How much? 56634. So 56634 or minus plus this delta H of the product is equal to 0. So we are going to have an expression in AT cube plus BT square plus CT plus D equal to 0. Okay, so you can solve this equation. Okay, so solving this equation, we are going to get different roots, right? If it is t cube, we are going to have different root. What, take the positive root. Positive root will give us this cubic solution. This cubic equation can be solved, and take the positive root, we are going to get what is t. Okay, so we are substituting t in Kelvin, so whatever you are getting, that is going to be your temperature in Kelvin. Okay, so please calculate the temperature and comment your answer. Okay, please comment your answer. Let us check it. Okay, so how to solve this? Please use your mathematics skills. Okay, so you have to simplify this expression. Okay, so how many t terms are there? How many t square terms are there? How many t cube terms are there? Okay, so use these terms. You will have here one t term, here one t term, here one t term. So take them commonly outside. Similarly, here one t square term, t square term, and t square term. Club them together. Similarly, t cube term here, here, and here. So there are three t terms, three t square terms, and three t cube terms. Sum them and take the coefficients and solve the problem. Okay. You should get value between 1000 and 1200. So in this lecture, we have solved some numericals on adiabatic flame temperature, how to determine adiabatic temperature if XSAR percentage is given using the CP expressions as a function of temperature, right? So also we have, if CP mean is also given, in that fashion also you can determine adiabatic flame temperature if XSAR percentage is given. So reverse numerical, where adiabatic flame temperature is given and we have to determine the XSAR percentage. Such numerical also has been solved in this lecture. So these topics will be part of our evaluation for minor 2. Okay, please complete all the lectures and try to solve the numericals and practice some model numericals also. So in the next lecture, we will start the next module where we will discuss about what is ideal solution, what is Raoult's law, how to determine vapor pressure. Okay, and then we'll move on to the topic of humidification. What is humidification operation, how to define desaturation, percentage saturation, all that. Okay, so and we will learn about how to make use of psychometric charts. If two data is given, how to get the remaining data using psychometric chart, that will be discussed in the next lecture. Okay, so that will be the end of our syllabus with the topic. Okay, if you have any doubts, please comment and contact me, and if you have understood the concepts, please leave a comment. Thank you for joining my classroom.